Hello, everyone, and welcome. My name is Rula Deef. I'm a senior principal at Geosyntax Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. This webinar will consist of a brief overview of both programs, followed by technical discussions on munitions, mobility, and burial in underwater environments. Today's webinar features Dr. Joseph Calantoni of the U.S. Naval Research Lab, who will present results of field and laboratory experiments performed using surrogate and inert certified munitions in underwater environments. Joe will also summarize a conceptual understanding of the science behind the modeling and will discuss the design of future demonstrations of modeling technologies for Uxo site management. Joe will be the only presenter today. He will pause halfway through his presentation to entertain questions from all of you, and we will conclude the webinar with a second Q&A session. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and also provided to you in your webinar registration confirmation emails. If you are unable to download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free account. If you continue to have difficulties with the slides, or if your screen freezes, try keying in Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, follow the steps outlined here. Click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, feel free to call into the conference line shown here. You may also submit a comment using the chat box function in Zoom, but only use that chat box for comments related to technical difficulties because we like to use the Q&A option for submitting questions to today's speaker. Just a few quick reminders. You can always download a PDF of the slides at the link shown here. This is the webinar webpage dedicated to today's webinar. And by downloading the PDF and calling into the conference line, that's another way you can participate. A final way to view the slides and hear the audio is to join the live stream option on the SERDP and ESTCP YouTube channel at the link shown here. Today's broadcast will be listen only. We have over 200 people calling in today. So the way to submit questions is again to use the Q&A box in Zoom. You do not need to wait until the Q&A periods to submit your questions. We do encourage you to submit them well in advance of the Q&A sessions. And we ask that when you submit your question, please make sure to add your organization name at the end so that we can identify it during these Q&A sessions. And with that, I would like to introduce Dr. David Bradley, who is the SERDP and ESTCP Program Manager for the Munitions Response Program area. Dr. Bradley's professional career includes U.S. Navy-supported research, laboratory directorship at the NATO Undersea Research Center in Italy, and research and academic activities at Penn State University's Applied Research Lab. As an emeritus professor of acoustics, he's done fantastic work in this area, and he also currently serves as a University of Washington APL staff member assigned to the SERDP and ESTCP program office. Dr. Bradley is a fellow of the Acoustical Society and has chaired society committees and served as president. Dave, thank you so much for all of your fantastic work, and please proceed.
Thanks, Rula. Welcome everybody to the webinar today. I, like you, look forward to it. SERDP and ESTCP are now approaching the third decade of a partnership between Defense, Department of Energy, and the EPA. SERDP in particular has a focus more on basic research and advanced development. ESTCP, on the other hand, has the primary goal of a focus on getting hardware into the field and being used in programs that require that kind of expertise. There's 4 programs in SERDP, and there's a 5th one that is only in ESTCP. Listed here are the 5 programs. I won't read them. The one that's unique to ESTCP is installation, energy, and water. Today, of course, our focus is on munitions response. The history of munitions response has been focused on land, and within the last 5 years has transitioned, although work continues in terrestrial efforts, but the focus in the program has moved to underwater circumstances. The underwater in this case has a kind of a loose definition of water deep enough that recreational divers could perhaps encounter something like you see in the photograph in front of you, which is not something you would want them to do. The next 3 slides, I'll let Laura spool through. They relate to the seminar series, and of course, a most hearty welcome and an invitation to attend our symposium, which will this year, like many things, be a virtual one in late November, early December. With that, I will turn it over to Joe Calantoni, and I look forward, as you will, the moment he starts to talk on the work that he has been doing. Joe?
Thank you, Dave.
Thank you, Dave. Yeah, Joe, let me just quickly introduce you and I'll turn it over to you. Today's speaker is Dr. Joseph Calantoni, who is currently a research physicist at the U.S. Naval Research Labs Stennis Space Center. Joe also serves as section head of the Sediment Dynamics section and the acting branch head of the Seafloor Sciences branch of the Ocean Sciences Division. Joe's research focuses on understanding the physical, mechanical, and acoustical properties of seafloor, estuarine, and riverine sediments through a combination of mathematical and numerical modeling, detailed laboratory measurements, and field experiments with military applications in mine warfare, naval special warfare, and the burial and mobility of unexploded ordnance. So clearly, Joe, you're an expert in this field, and your work with SERDP and ESTCP has led to the 2015 SERDP Project of the Year Award in the Munitions Response Program area, which Dave leads. And just a little background about Joe's education. He has a bachelor's degree in physics from Penn State University and master's and doctoral degrees in physics also from North Carolina State University. Joe, the floor is yours.
Thank you, Rula. Thank you all for attending the webinar today. By the count I see on my screen, there are some 200 participants in the webinar today. That's fantastic. I want to just take a second and thank Rula and her team for the excellent job working with me to put together these slides. Very professional setup. I hope you will all enjoy the talk today. And I want to thank Dave Bradley as our program manager here, and also Herb Nelson, who was our program manager before him. These guys are 2 of the best program managers that I've had the pleasure to work with, throughout the Department of Defense. And must thank Mike Richardson and Mike Tooley, the 2 science advisors to the program as well. I think a lot of what you'll hear me say today are probably echoes of conversations that I've had with the two of them over the years. And they both gave me some guidance and advice when putting together the outline and the abstract for this webinar today. So let's go to the next slide. Let's see if I can take control of the screen here. There we go. So the agenda, I broke the webinar into two parts, and the first part is going to focus on existing knowledge, observations, technologies. It will include a lot of slides from colleagues of mine that have graciously contributed their work for me. I thank all of you, and I will try to call you out when I talk about your particular slide or work. And there is a slide of logos at the end that tries to mention the organizations for all the folks who helped contribute something to this webinar. The second part will focus more on a project that we have ongoing that I am the PI on at the U.S. Naval Research Laboratory. And for the site managers and folks involved in that side of the work that are on this webinar listening, I think you will get the most out of the second part of this webinar, but I encourage you to hang with us through the first part, and I hope you will learn something new that you didn't know maybe about the science of mobility and burial. And so I have to mention my project team for the current project, MR19 1317, Mr. Ed Braithwaite. He's been co-PI with me through all of the SERDP and ESTCP work that we've been doing since going back to, I guess, 2012, 2013. Alex Sheramet at the University of Florida has also been a co-PI with us. More recently, we've been working very closely with Dr. Hockey Klamler and Scott Wassman, who are both through the University of Florida. These guys are geotechnical engineers, and you'll see their contributions to the work later. And then key members of the team right now, Chuck Key, Sam Griffith, and our postdoc Carter Duvall really provide the electrical and mechanical engineering support, the geology, sedimentology, and all the signal processing that it takes to go into, collecting and then analyzing this data that we're going to show you today. Okay, let's move on. So, question to start for everyone. Do UXO wash up on the beach? I'd like everyone to try to answer that question right now. Write it down on a piece of paper. Yes, no, maybe. What do you think the answer is to that question? And we will explore that question and the science behind that question as we go through this webinar. And we'll see if you agree with me by the time we get to the end of the webinar or not. So hopefully everybody's picked an answer, what they think, yes, no, maybe, and we can move on. This picture that you're looking at on the left is the Swash Zone. That's the area of the beach that's constantly wetted and dried by the water line at Duck, North Carolina, at the U.S. Army Corps of Engineers Field Research Facility. And you see some debris, if you will, laying there on the beach. And the picture on the right is a close-up of one of these UXO that appeared on the beach back in July of 2016. And so I think it's very typical to want to say, well, was there a storm? Did these things wash up on the beach? It just seems like a natural reaction. And in this case, in fact, July tends to be a pretty benign time of year in terms of the energy of the coast there. And there was not an early season hurricane. And so this is something that happened under rather benign conditions. And so how did this happen? So let's look at the next slide. So what you have here is cross-shore distance. So going from the FRF facility and walking out onto the beach and out into the water. And they have this vehicle called the Crab that they drive out to do these surveys. And so you have about 300 meters of cross-shore distance on the horizontal axis, and you have about 10 meters of range and elevation on the vertical axis. And the color is actually dates by time. And so you see 35 years of profiles that were collected. And that black dashed line is the profile collected on July 26 of 2016 when those UXO appeared on the beach. And so what was actually happening was a retreat of the shoreline that was part of a larger feature that was migrating along the coast of North Carolina. So this was really a function of the larger scale geology that drove the exposure of the UXO in this case. But the point is, they were buried there. They were always there, and they just became uncovered. And so in this case, they definitely did not wash up on the beach. And I would argue, and I think we're going to present a pretty strong case today, that that is actually what happens most of the time, that these things do not travel a long distance and make it to the beach in that mode. Rather, they were always buried nearby and became exposed during some kind of event. Okay, and I need to thank Meg Palmston for providing these slides for me, and of course the folks at the FRF for the data that they provided. So before we get into it, I just want to give like a higher level of the approach that we're trying here. And this is not an uncommon approach to solving difficult interdisciplinary problems, but you have theory, and we will talk a little bit about the sort of physics behind mobility and burial. And then in the bottom left, you have observations, and many groups are making different observations, and we'll talk about a lot of those today. And then you have models as well, and people are developing models. And so where you really want to be is at the intersection of all these circles, right? And so you start with some theory, you're out on the edge of the circle, and you start to push towards the center as you bring in observations and models, for example, or vice versa with the other two. And so this is the approach that we take in the work that we're trying to do for the Munitions Response Program. And I think if you look at the portfolio at a higher level, this is really the approach that the program office has taken as well. And while I have this picture of the beach behind me, I'm going to use it for a second to define something. So I'm going to bring my pointer over. And if you look at this area right here, I mentioned this earlier, this is what we like to call the Swash Zone. So that's the area of beach where it's constantly wetted and dried. You see this white breaker line that goes behind the red circle. That is the area of the beach that we like to refer to as the surf zone, where waves are actively breaking. And then if you go out into deeper water here, where you start to see this first bump of the waves coming in, this is the beginning of what we might call the shoaling zone, where waves start to feel the bottom and interact, and they pitch forward and eventually break into the surf zone. And the important point I want to make is this kind of depicts a more typical benign day. But when you have big energy and big storms, this surf zone can get really wide, and the energy can be distributed across a large cross-shore distance all the way out past this area here. And a lot of the observations I've made have been out in this depth to the right, but during storm events where the waves are now breaking out here at this depth. Okay, and so we'll talk some more about this. So let's talk a little bit about our hypothesis. This is the hypothesis that I've started with, when I first started thinking about this problem nearly a decade ago, and that is that the density of the munition is really the key factor to understanding what the fate of the munition will be. And so let's unpack that a little bit. When I say the density of the munition, I don't just mean the weight of the munition, I mean the weight of the munition normalized by its volume, right? So most of us, the human body has the density of, very close to water. This is why we don't immediately sink to the bottom of the swimming pool like a rock. And of course, a rock has a density that's more than 2 to 3 times the density of the human body. And that's why it sinks right to the bottom of the pool. And so you can non-dimensionalize the density of the munition by the density of water, by the density of sand, by the density of water sand mixtures. And so you will get slightly different numbers for this S variable that I have on the screen here, S sub M, so the M meaning munition and S being the non-dimensional density. But the fact is that the trend is always going to be that as S sub M increases, your likelihood for burial, which is depicted in the picture on the bottom right, down here, will increase. And I've colored burial as green, and I'm sure site managers will appreciate that because burial is a good thing, right? We like when things are buried and not moving around and being exposed for the public to interact with. And so mobility, I've colored red, and when things are less dense, they're more likely to be mobile. And we'll get into this more with the data as we go through the presentation. So a couple more definitions. We're going to talk about initial mobility. And so the graphic on the left is from Landry and Garcia in their laboratory up in Illinois. And what you see is the munition is starting to roll towards you in the image as you go from top to bottom. And the picture on the right, I took from the Encyclopedia of Coastal Science. And don't ask me about the scales or the details of this image. What I want you to take away from this image is that there's something that we define as scour burial. And that process has a limit to the depth that the object can be buried. So what happens, as you see depicted in this picture, is that the waves and the currents create a pit around the object that eventually the object will slide, roll, fall into, and be captured. And the important point is that this object has a limit to how deep it can be buried as a function of scour burial. Scour burial will always leave the object very near the surface. So it will either bury roughly flush with the surface, perhaps a little bit of it will be sticking out, or it'll be buried just below the surface, some small fraction of its caliber or diameter below the surface. Later, we'll talk about extreme burial, where things can be buried many diameters, many calibers below the surface, feet below the surface, due to the interaction from the waves. And that's a different process. And I just wanted to distinguish that here. So, density of munitions. Turns out that if you believe my graphic I showed you a couple slides ago, and then you go and interrogate a lot of different surrogate and inert certified munitions, you will find out that they have a density that makes them want to bury. And so here we went to Blossom Point. Thank you to Dan Steinhurst and Glenn Harbaugh. We measured 70 items that are all laid out in the picture across the top. And they range from inert certified to simple surrogates. We built CAD models, we weighed these things, we used a laser scanner, and back to my non-dimensional parameter for density, 95% of these items, as they were laying on the floor there, not filled with any explosive or anything else in some cases, have a density that is going to make them want to bury, to always want to be tending towards a state of burial. And so this gray line that I've put sort of across the graphic on the right, the bottom right, that depicts kind of the range of this SM variable depending on how you normalize it. So now we have density in as a dimension quantity here on the vertical axis in kilograms per meter cubed. And sort of anything in that gray range and above it on the plot is very likely to be buried. Okay, so this made us wonder about all the rest of the possible munitions that could be out there. And if you've tried to get data on munitions, you know this is difficult to do, and particularly sort of the density, which seems like a bit of a scientific, esoteric piece of information that somebody who just needs the thing to go boom does not care so much about. But we looked in the Army technical manuals, and for those of you who know what they are, you will appreciate the work that we did here a little more. If you don't know what they are, that's fine. You just need to understand the result of what we're trying to capture here. So let's take the 155 millimeter howitzer round, for example, as what we're looking at here. If you look through the manual, there will be something on the order of 40 to 45 different entries. Each entry has a couple pages. And there are a lot of details about, you know, a particular howitzer could have high explosives, it could be packed with grenades, it could be a flare. And so, and they have variations of nose cones and fillers. And so what we did here was actually go through for each entry in the manual. So every different type that's called out with a 1 or 2 or 3 page entry, we constructed a probability distribution using all of the perturbations that were possibly made for that type of munition. And then in the graphic you see on this slide, we combined all of those distributions together into one single overall likelihood distribution for the 155 millimeter caliber. And in this case, the important point is that the vertical red dashed line, that's sort of the top of the gray bar that I showed you in the previous slide, and everything is to the right of that, and density is on the horizontal axis. So all of the permutations that you could possibly imagine for the 155 millimeter caliber fall into this category where they really want to bury. They don't want to be mobile. And some of you are maybe scratching your head going, well, how can something bury on my coral reef? And that's an excellent question. And so if I haven't, caveated this at the top, we are talking about sandy sediments here, and particularly the work is applicable to all kinds of mixtures of sand, I believe. If you have strictly mud, I actually think the problem's easier, and you can ask me a question about that when we get to the Q&A. But if you have a coral reef, that's a unique problem, and we're in a different realm there. So we have constructed these kind of curves for other calibers, and the important point here is if you know what was fired at your site, if you have good firing records, you can go right to that specific caliber, look up the density distribution, and immediately know a lot about what you expect the behavior, the phenomenology of the munition to be at your site. Even if you don't know the specific type, if you just know something, like we know they'd fired a lot of howitzer rounds here, but we don't know the details of what kind. This overall graphic will tell you a lot about the phenomenology of the howitzers that were fired at your site. So that's the important message here with this slide. Okay, so let's talk a little bit about mobility and burial observations. So there have been a lot of observations made on the initiation of mobility. So what does it take to get a munition to sort of roll out of its pocket and start to be mobile on the bed? And then I also talked about Scour Burial. And so there are definitely a lot of observations on Scour Burial. Here are 2 graphics that I've borrowed from our colleagues, Sarah Rennie and Alan Brand and Carl Friedrichs. This is published in Ocean Engineering, so you can go read more details about it. But what we're looking at is a fit to data. So I'll call this empirical knowledge that's been compiled. And what we see is encouraging in that the behavior does follow a power law and can be pretty well characterized with a fit across this range of axes that we see here, a couple orders of magnitude on each set of axes. And so this is very encouraging, and these kind of models can be very useful for making probabilistic predictions. And this is exactly what they're trying to do with it, is to incorporate these into the UNMES model, which some of you may know about and we'll talk a little bit about later. But these types of formulations are really valuable, and they're out there, they exist. There's been a lot of observations made that can help you understand what is happening with the munitions, or what might be likely to happen with the munitions at your site. Okay, so let's talk a little bit about technologies that have been developed under funding from the Munitions Response Program. And so here I've got what I'll call a smart surrogate munition. I think this is probably one of the simplest versions of the surrogate munition. This is one that Ed Braithwaite designed and fabricated. He's the one holding the cylinder in the picture here. And what you see in the bottom right is a commercial inertial measurement unit, very compact, small commercial measurement unit that we've sort of hacked into a massive pack of lithium batteries. And we put it into the shape. If you look at the pictures on the left, the far left is a surrogate for an 81 millimeter mortar, and the one next to it is a surrogate for a 4.2-inch naval round. And so these things have roughly the right density and the right aspect ratio, and they're instrumented with this IMU. It gave them about 3 to 4 weeks of recording time at 16 hertz. And so we are recording all the roll, pitch, yaw, slight motions of these things as we put them outside the surf zone. And I'll show you the results from the experiment we did with these in a little bit. But there are other versions. So depending on what your needs are, what area of the beach you might be working in, you may want to instrument your munitions, your smart surrogates in different ways. Here's a group of examples from our colleague Jack Paleo at the University of Delaware. And Jack has added many more instruments into some of the surrogates here. And primarily, it's motivated by the environment in which he's trying to capture data. So in Jack's case, he's working in that Swash Zone area where the beach is constantly wetted and dried, and you have really strong accelerations and impulsive forces that can act on your munitions. And so you require some different sensors to capture the behavior. Of course, it gets exceedingly difficult to instrument these things as the caliber gets smaller and smaller. Here's another great example. This is from Diane Foster at the University of New Hampshire. And in this case, she's mapping the pressure distribution in the time domain around the surrogate item that was placed on the seafloor. And you see the little penny in the image on the left, the bottom right of that package of images. You see the penny showing the size of the sensor that was put into the wall of the cylinder. And the thing that you might be wondering is, why do I care about the pressure distribution across the munition? And so, you know, on the science side, on the S&T side, we have to develop the knowledge about the pressure, because it's really what drives mobility and burial in these impulsive sort of wave-dominated environments. And you see what she's able to do with this is map out the pressure. The picture on the right shows a map of this pressure distribution. And what this is going to lead to is better models for us to know the rate of burial, the time it takes things to bury. And if we go to the next slide, we see a couple pictures in the bottom left. This was inside near Fort Foster in Maine. You see the red dot depicts the location of the observations. And over a 2-day period, she sees the cylinder burying. And this is a really unique time set, really valuable data set. We've got the timing and the rate of burial was directly observed. And it's confirmed, those numbers are confirmed by photographs that were able to be taken during daylight hours. And then, of course, they continued to observe into the evening. Okay, another instrument set this is a commercial package. This is from Vemco. This was Art Trebanis and Carter Duvall used this at the University of Delaware. And down in the bottom left, you see these very small, there's no scale there, but if you look at the munition in the bottom center image, you look at the tip and tail of the munition, you see a little black dot. That is where these little sensors are embedded. And so these are acoustic trackers, and they have really long endurance. And I'll just skip to the punchline. They're able this was work done in Delaware Bay in sort of a more muddy environment. And they're able to track the positioning, you know, by tracking the two ends. In the bottom right, you see the graphic there, tracking the two ends of the surrogate and, you know, getting its positioning down to below 20 centimeters accuracy over really long periods of time. And so this is a commercial technology that's available for tracking munitions. One more piece of kit I want to talk about. This is from Peter Trukowski and his colleagues at Woods Hole. This started as something Peter called the Jet Yak, and I think has evolved into this surf zone capable autonomous surface vessel. And so it's got a USBL acoustic array. It has a single beam echo sounder. So in addition to geolocating your targets that would be emitting some small signal, like in the example I showed you previously from Vemco, You're also mapping the bathymetry, and this thing is designed to go in the harshest of environments, to go through the surf zone and be able to handle it. And so this is a really great piece of technology for not only mapping out your shallow bathymetry, which we all know can be very difficult to do, but also for tracking objects that you placed out there as surrogates and want to know what their phenomenology and behavior is. I want to show you a little bit of data from the Wallops Island munitions mobility experiment that we performed. So back to, I showed you a picture of an 81 millimeter mortar that we had instrumented with an IMU earlier. And so what happened here was a storm came through, and over roughly a 10-hour period, the munition, the smart munition became mobile. And so we have over 570,000 data points that we integrated over. And by doing the raw integration, we ended up with a displacement of 62.9 meters on a heading of 344 degrees. And this was work that Danya Frank did, who was our postdoc at the time. We worked with divers. We found this object. We measured it with a tape measure underwater, and the divers, using their instrumentation, got 61.6 meters on a 340 degree heading. So we really nailed it, if you will, when integrating the IMU displacement. And the thing that this buys you now is, now you actually can watch the entire 10 hours of this munition rolling back and forth as it slowly tries to make its way towards the beach. And it did try to do that. And we'll talk about why that happened. But what I want to show you here is, on the left, you have every half hour, as you go from the bottom of the picture to the top of the picture, you see both the frequency spectrum of the waves and the IMU. And so the rolling moment of the smart munition was rolling with the waves and tracking it. And so that was really kind of exciting and interesting piece of data that we got there. Okay, and one final piece of data I want to show you. This is from the laboratory. This is Jack Palayo's in the Swash Zone. And this really just highlights, again, this importance of density. So as you go from green to blue to the stainless, which I believe is the purple color, you see the water rushes up to the top of the picture as the swash inundates the beach, and then it comes back down the image. And you see, as things are become more and more dense, they're less and less mobile. And it's harder for the swash to push them on shore. And so typically what happens here, the fate is they either are ejected out of the top on a random swash event, or they get captured at the toe. They migrate down towards the toe, the beginning of the swash, where the swash starts. And so this is some data from Jack Palayo. And I do have one more data set. So I am running long on this first half. Let me get past one more data set to show you. So we did I mentioned extreme burial. So let's talk about the extreme burial then. Here is a rig that we deployed on the right. This was off of Duck, North Carolina. And you see in the image here, the pier is depicted here. And our location of deployment was probably right at the corner of this inset here. And we had an incredible amount of wave energy. This is the wave frequency spectrum here. This is the significant wave height measured in 8 meters of water here. And I'm going to focus on this very large event with over 5 meter significant wave height, and the frequency spectrum is saturated here, which means the waves were effectively breaking over the top of our 8 meter array, which is depicted on the graphic on the right here. And at this location of the arrow, Jesse McNinch provided 35 years of seafloor elevation data. And what you see is that the bed literally just oscillates up and down, not more than a foot. And we saw pre and post experiment 5 centimeters of change in elevation at 8 meters. But we observed up to 2 feet of burial for our surrogates that were out there. And so this graphic here has non-dimensional density on the horizontal axis. And now we've non-dimensionalized the depth of burial by the caliber. So these numbers here represent how many calibers or diameters of the object deep they were found buried. okay? And this, leads us to believe that density and caliber are really the most important characteristics, and we'll talk a little bit more about that in the second half. And so the last graph I want to show you, I think this really summarizes things. Peter Trakowski has done a great job of really pulling a lot of stuff together and kind of summarizing the state of the art here with this. And what you've got, again, is non-dimensional density on the horizontal axis, and now you've got wave velocity on the vertical axis. And, this is the velocity effectively of the fluid near the bed generated by the waves. He also includes a factor for how quickly the wave velocity increases, so how fast is the storm coming in? And that's illustrated by these different curves here with the 0.1, 0.3, 1.1, and 3.4. And you see the data I just showed you from Duck would be up in this upper corner here. And some of these objects here that are in green are much lower density in this case. This is just less than twice the density of water. So the density of sand is somewhere out over here, around 2.5 on Peter's graphic. And so I think graphics like this, taken in the right context, can be a valuable tool, just as they are, for giving you a first kind of order of magnitude understanding of what can be happening at your site. Okay, so the summary really is just the bottom line, that I hope you believe that collectively we've developed a really strong understanding of munitions phenomenology, and there's still a lot of work ongoing as well. And so I am over time, and we will take some questions now.
Thank you so much, Joe. We have a lot of questions that came in. We're going to start with one from the Navy. How did you model the effects of impact at speed versus a more gentle placement of the units? And if this is something that you're going to cover in the second half of the presentation, we can wait. But why don't you go ahead and try to take a crack at this question?
So I think the question is asking, what the role of impact burial is. And we did not model impact at all in any of our experiments. In fact, I think we go to quite a large effort to try to very carefully and gently place our surrogates onto the seafloor. And I believe most of my colleagues do the same. And then we let nature take its course and bury them. And I think if you track along the story that we've been highlighting here about the role of density and the propensity of munitions to have large values of density that put them in a category that always want to bury, I would argue, I apologize to who might not agree to begin with, but I would argue that impact burial is not quite as important for the final fate, except in the cases of softer sediments where they are immediately buried deep into the sediment. Anything that's partially buried in sandy environments by impact is going to follow the physics that we just outlined and either become mobile or become fully buried pretty quickly.
Wonderful, thank you, Joe. The next question is from the Environmental Protection Agency. How does long-term corrosion affect munition density?
Yeah, that's a great question. I don't know that we really have a good answer for that, right? So certainly you can imagine if all of the filler is leached out over time and perhaps replaced with seawater, that would change the overall density. The major contributor to the bulk density in most cases is going to be the steel case, inevitably, that almost all these munitions have around them. And so unless you have breakup or a substantial deterioration of that casing, I suspect it's going to have a minimal impact overall. But I think this is really an open question that hasn't been well addressed yet.
Thank you. And another follow-up question from EPA has to do with the location of your demonstration sites. You've showed a variety of examples from the Munitions response program area at SERDP and ESTCP, but specifically, are you aware of any West Coast demonstration test sites that you can reference or here?
Okay, that's great. So yeah, I think the majority of work that I've shown has been on the East Coast and in the Gulf of Mexico. But the experiment that I will talk about that hasn't been performed yet, that's scheduled to start in December, in the second part of this webinar, is focused on the West Coast. It is going to take place right offshore of Camp Pendleton in Southern California.
Great, thank you so much. This next question is from Fort Belvoir, the U.S. From the U.S. Army, and it has to do with your conclusions that you showed on the last slide. Are they the same for a fine-grained substrate versus the other substrates that you discussed?
Simple answer, I believe yes.
Great, thank you. All right, this is a question from the University of Delaware. Can you describe the interactions of the munitions and bed forms or ripples? What would be the role of density in this situation?
So that's a unique situation. I think that if you have active bed forms, then you are squarely in what we would call the Scour Burial regime. And if you go back to the slide that I showed from Sarah Rennie and Alan Brandt and Carl Friedrichs from their ocean engineering paper, the graphic on the right-hand side, the upper right portion of that graphic, depicts Scour Burial behavior in the live bed regime. And I think that's exactly what you would have. Now, you may have times when, because of the migration of the bed form, the surrogate or the munition will be more or less exposed, say, to sensing technologies that might use high frequency and just see the surface and not penetrate the sediment. And of course, trying to find objects among that are partially proud among a sand ripple field with any technology can be challenging. But yeah, I think that this just falls right into the active bed scour burial regime that's described pretty well by Carl and his colleagues.
Thank you. We'll do two more quick questions before we let you finish your presentation. This is a question from Arizona State University. Aside from on-site testing, is it possible to use computational fluid dynamics to predict Uxo mobility and burial? And if yes, what would the challenges with this numerical approach be?
So I believe it is possible to address this with CFD modeling, and there are at least two projects that I can think of immediately that are funded by the Munitions Response Program to do exactly that. And so you have to remember, when you go into the CFD domain, you do limit both the size in terms of spatial extent and the duration of simulations that can be performed. So detailed numerical simulations can be a really valuable tool to help us close the loop on some of the, say, unknown parameters in our more mesoscale or empirical approaches or probabilistic approaches. But they are not going to be able, in most cases, I think, to predict over an entire storm event, for example, or over a whole season. And so they have a place, I think, in what we're doing. And I did kind of purposely leave them out of the webinar today. I apologize. But yeah, there are approaches ongoing, and I think they definitely add value to that sort of holistic picture I showed early between the theory, the modeling, and the observations.
Great, thank you. This is a question from the Virginia Department of Environmental Quality. Is an estuarine environment that you discussed, the scour burial, is it limited to the scour burial issue? But or does sedimentation play a role? And if it does, how do the models that you described address sedimentation?
Yeah, sedimentation is definitely a great point to raise here. And certainly there are environments where sedimentation can play a role, as in estuaries in other parts of the coastline, rivers as well. The models that we've discussed so far, I do not believe are capable of addressing the sedimentation issue. However, I will talk about a model in the second session that is capable of addressing the sedimentation issue. And I'll leave that for the second session.
All right, well, this is a good segue to let you continue on with your presentation. And for those that have asked questions that we have not gotten to, we will get to them at the end. So Joe, please continue.
Thank you, Rula. Okay, so here is the agenda for part 2 of this webinar. And this is more, I think, a outline for how, or what I believe, I should say, are the main ingredients needed to perform demonstrations for modeling technologies. And so I'll kind of go through this list, and I will talk about some of the bullets in more detail later, and some of them I won't talk about later, and I'll just address them here. So you have to perform environmental characterization. I believe you have to choose some of these surrogate technologies and utilize them in a way that best helps you understand what you need to manage your site in particular. You need to utilize some prediction models, and they could be as simple as, empirical fits like we looked at the early part of session 1, or a graphic like I showed near the end from Peter Trukowski that kind of gives you a more synoptic view of the phase space between the density and the hydrodynamic forcing. Or you could do something more detailed like we'll talk about near the end of this second part of the webinar. I think you're going to have to predict and maintain the infrastructure over multiple seasons, maybe even years, to really provide the kind of data needed that I think is likely to be needed to satisfy regulators, for example. And then finally, we get to the scoring and evaluation piece. And I'm not going to say anything about that other than to make a plug that I know Shelly Cazares is going to give a presentation at the symposium this year about scoring and evaluation of demonstrations. And so I think we should all try to tune in and look forward to that. So the problem statement that the current project I am focused on for the Munitions Response Program under SERDP is how to demonstrate the capability that we have to predict munitions mobility and burial in underwater environments. That leads us to talking about the timescales and locations, which I mentioned. What are the appropriate metrics for success? I know as academics and as researchers, we may have a certain set of metrics that we think are important that need to be met to consider our models or our techniques valid. And those are likely to differ from what the legal and the regulatory folks who are an important part of the process that site managers have to go through. And so how do we rectify those differences? These are questions I don't know the answer to yet, and probably won't be able to give you an answer before the end of this talk, but these are things we need to think about. And finally, quantifying the risk for long-term site management. So how do we quantify risk in a way to help managers make the most informed decisions that they can? And I think those last 2 bullets are really sort of interconnected. So the overview of our ongoing project, the real objective for us from the science side of things is to try to reduce the dimensionality of the problem when it comes to the munitions. So I tried to make the case during the first half of this webinar that density and caliber of munitions are likely to be the most dominant characteristics that you need to know to make an assessment, make a good faith assessment of what the final fate of your munitions are likely to be. And there has been a lot of obsession, I know, by myself and many of my colleagues over all these other details of the munition, like the fins and the tapers and the rolling moments and the center of mass. And I would argue that I have come to believe all of these things are just going to provide a small perturbation to what the final fate that I think we can predict just by knowing the density and the caliber well. And that's what we're trying to design an experiment to do here. As part of our technical approach, we're developing some new geotechnical models and creating some novel surrogate munitions, and I'll talk about those. And of course, our long-term goal is to try to provide some guidelines to help us get towards these demonstrations that we want to do for mobility and burial modeling. Okay, so we started with some environmental characterization, and this is offshore of Camp Pendleton. And the important point here is that, if you're a site manager thinking about how do I do environmental characterization, I would argue that, some large percentage, it's more than half, maybe as much as 80 or 90%, depending on where you're at in the world, public data sources are going to give you most of what you need to know. And, you need things like bathymetry, you need to know something about the sediments, and you need to know something about the hydrodynamics that are forcing your site. And so in this case, we've got public data in the upper right here. This is waves. We've got bathymetry that we downloaded off of the web. That's on the left side. And then the data that we added is in sort of the middle of this slide here, where we have some side scan imagery and the little pies that, for somebody of my age look like Pac-Men. Those are little charts that tell you what the percentage of sand, silt, and clay were at each of those locations where we sampled. And so this is some of the data that we're starting with. And we're going to go out in December and we're going to put out some instrumentation. So on the left, these are smaller platforms, and these are designed to observe waves and currents. This is what I like to call our far field forcing. So this provides sort of your offshore boundary condition, if you will, or boundary conditions. And then on the right side, we have these larger, kind of more imposing platforms that can house many instruments. And, I mentioned high frequency sonar imagery will be collected here. We'll also measure other characteristics of that wave velocity that Peter Trakowski plotted in his diagram. And so this is what the layout is going to look like for our upcoming experiment. 3 of these smaller moorings going offshore out to the 20-meter contour, and we're going to be working roughly between the 5 and 10-meter contour with some target fields. So let's talk about our surrogates here. So this is work that's come out of collaborating with Scott Wassman and Ed Braithwaite and Chuck Key, our engineers, with help from Carter Duvall, have all been working together on this. And so what we're trying to measure are the pressures inside of the seabed. And so we're using combinations of what's called a pore pressure sensor and a total stress sensor. And you see I actually have a little bit of math on this slide. But the important point is that we are trying to provide time domain observations of the phenomenology. So, we posit that this extreme burial happens due to momentary liquefaction, or the degree, what we like to call the degree of liquefaction of the seabed. So that means that the waves create such a large negative pressure right at the seabed that it actually dilates the bed and allows objects to sort of very quickly percolate down through the seabed. And so we're trying to observe that process directly with these instruments that are going to be mounted into a surrogate munition. One of the caveats is that this requires some pretty intense calibration. And so this is Scott Wassman's rig at the University of Florida. And on the right-hand side here, you see their centrifuge. And so at the left side of the arm that spins, you will pack your sensors with sediment. And the idea is that you need to rotate the centrifuge up to speeds that will provide pressures that are comparable to what you expect to find based on both the water depth that you will be operating in and the expected wave climate. Additionally, you need to pack them in with sediments that are, if not taken from the location where you're going to deploy, representative of that distribution of sediment at that location. And so just the calibration process here is quite involved. Now, what do one of these look like? So in the upper image here, we have our cylinder. This is for the 81 millimeter mortar caliber that we're trying to represent. And so there's a lot of instrumentation in there. A lot of it is occupied by batteries, and then we accomplish the ballasting that we need by varying the materials of the end caps and the cylinder itself. And so the idea here is to do 3 representative densities, which you see in the table in the bottom, and what we're terming a low, medium, and high. And those descriptions of low, medium, and high come from creating one of these likelihood probability distributions that I showed you earlier for the 81 millimeter mortar. And in the middle of the slide, you see a picture of a inert certified 81 millimeter mortar. And so the idea is to deploy 3 of these surrogates that are heavily instrumented with a range of densities alongside of a detailed inert certified munition, and watch for the extreme burial, and do all of these 4 different surrogates that we will deploy follow the physics that we expect, that we looked at in the first half. And if we can arrive at that position across a range of 4 different calibers that we plan to deploy, I hope we can convince most of you that for wave-dominated environments, at least, where things are can be very energetic, that these details beyond the caliber and density of the munition are likely to not be very critical to your problem. So I'll talk a little bit about our dynamic seabed model. And so this is Hockey Klamler's work. And so what you're assuming here is a force balance on the UXO. And without getting into the details of it, I probably should have put a citation here. We have one publication that is out in the Journal of Oceanic Engineering. Dr. Klamler is the lead author on that. You can find that and read sort of the first iteration of this model. We are on to the second iteration that we are about to resubmit for publication. And the important take-home point is that in the end, the predicted final burial depth is a linear function of the density ratio. And what you can do with this model is develop curves like these. And I apologize that we are missing, I think, I wanted to put an overlay. I will show you with my cursor where I wanted to put some overlays. So what you have here, the titles, the number 0, 1, 2, and 5 are meant to represent an initial burial depth. So you can imagine at 0, your munition is starting right along the top of your graphic. And at 1, it's starting right here at -1, and so on. And so one of the interesting things that can happen is that depending on the relative density of the munition, it can actually be buried at a less deeper position than it started based on a storm and based on its density. So things can become unburied without the seabed changing its elevation just by waves liquefying the bed. And the final burial depth is also very sensitive to where it starts. If it starts at the surface, it's likely to bury a lot deeper than if it starts already buried 1 or 2 diameters. And this red highlighted line is what represents the 90% degree of liquefaction. And that's, again, this concept that very large waves will generate very negative pore pressures on the bed to almost try to rip the bed apart. And so we kind of set the upper threshold at this 90% value for most of the big wave events that we've seen. And here we can calibrate this model. There is a calibration constant, K naught. We can calibrate it for our data from the duck experiment that I showed near the end of the first session. And the red dots here are the data from duck, and they sort of surround this 90% liquefaction line. And that gives us a calibration constant of 5. And now we've already started to use that in some analyses that we've done recently for an experiment that was performed off of Boston Harbor. Okay, so I'm going to spend the last few minutes talking about the probabilistic environmental modeling system. And so this is a munitions response project led by Meg Palmston and her co-PI Allison Penco. And so I was asked a question about sedimentation. This utilizes the model Delft 3D, and I'm not going to have time to get into the details of what Delft 3D is, but I will show you the next slide and we can talk a little bit about it. So think about forecasting, or in this case, hindcasting, oceanographic and atmospheric variables. So this model predicts waves, currents. It has the capability to predict morphology, so how the seafloor changes. It could predict sedimentation, and it needs to be coupled to regional forcing from larger scale atmospheric models or larger scale oceanography models. And this is, if you want to think about the operational forecasting that something like fleet numerical, if you know what that is, for the Navy, or the Naval Oceanographic Office does, it's this kind of operational oceanography is what I would call it, modeling. And so here we've got lots of details of the different nests. And so for those of you who do this kind of modeling, you know what that means. You basically model your domain at different scales until you get down to the really few kilometers of interest. And that's where you put your highest scale or highest resolution grid, which would be right here in the middle in this case. And so this is coupled with the underwater munitions expert system, which was developed by Sarah Reddy and Alan Brandt at the Applied Physics Lab at Johns Hopkins over a course of MR projects listed here. And so the idea is that you get your hydrodynamic forcing from Delft 3D. You also can get information about the morphodynamics of the bed. You combine that with whatever you know about the munitions, and you put that all together in UNMES, and you get some probabilities of burial or migration. And we'll look at what those probabilities look like here. And so here we've got comparing model and data, and this is for the example at Duck, North Carolina again. So this location right here that you see is approximately the location just north of the pier where we had our instruments back in 2015. And what this graphic on the left is showing you is, with this black dashed line here, is that over the probability of burial, over 70% of the munitions have a probability of being 100% buried. I believe that is what we're looking at here. And so the red graphic here, the color shows probability of burial. And you see there's some areas where things are just a little more or a little less likely to be buried. This was a very large event. And in our case, we found all of the surrogates that we put out buried. And that is very consistent with what this model is predicting in this first test case. So this leads me to, I hope, something interesting for the people on the operational side that are on the webinar here from the site management point of view. This is what I like to call my ConOps, or my concept of operations for site management. It's just a very high level set of bullets. But I think the essential pieces are here. And so, we talked about environmental data collection. The important thing is establishing data collection for environmental parameters. And these are not only important for understanding phenomenology of mobility and burial, but they're also important for understanding your instrumentation that's going to be deployed to survey, which comes up in the next bullet. So performing surveys to detect and classify. So those instruments also need to know something about the environment. And I will say here, I left it out of the presentation, but I do want to take a minute to note that the munitions response program has also been investing in some technologies that can help you do wide area surveys of things like sediment properties that are critical for these models, as you see, without having to go out and punch, hundreds or thousands of holes into the seafloor and take, many samples back to the laboratory and analyze them. There are some technologies that are being worked on by Todd Hefner at the Applied Physics Lab, the University of Washington, and by Nina Stark at Virginia Tech that I think both hopefully will really provide some excellent wide area coverage for us of these sediment properties and reduce tremendously the time and money it's going to take to characterize sediments in the future. But I did not talk about those today. So second bullet, surveys to detect and classify. You have to decide, what level of prediction modeling do I need? Is my environment very dynamic? Do I need UNMES and Delft 3D, or is a more simple graphic or power law representation give me enough information to make informed decisions? I don't know what we like to call on the Navy side tactical decision aids. I don't know what these look like yet for munitions site management, but there has to be some form, I assume, of tactical decision aids that all of this data feeds into, along with a lot of other information. And then finally, you have to, decide and make an action, and that the action could be to do nothing. But then this loops back into one of these earlier bullets. And this is what I think, long-term site management looks like at a high level. And so we'll go to the next slide. So just to summarize the second half here, I hope that I've convinced you that our understanding of the physics of mobility and burial has matured quite a bit over the last decade and continues to grow. There are a wide range of technologies and models that are being developed and in progress that are coming over the horizon, I think, very quickly at you. And when it comes to doing demonstrations for the mobility and burial modeling piece, it has to have a temporal component. And the really tough part is that there aren't really prior examples that exist. So, to draw the analogy to detection and classification, for example, there are analogies that can be made with work that had been done for many years on the land side. And certainly the temporal component is not nearly as important because things are positioned, a blind target field is set out, a test is done, it is scored, it is evaluated, and you move on from there. Whereas with the mobility and burial piece, you're a little bit at Mother Nature's mercy to what happens to things over time. And so it's a little tougher to decide how to structure these demonstrations. And I hope you guys believe that there are some strong benefits to DoD. I will just kind of skip past this slide. And acknowledgements of folks who have contributed to this webinar. Thank you all very much. And here's my contact information. So my phone number, and that phone number works even during COVID when I am not in the office. I encourage you to email me with questions. And if you don't get a response within a week, please email me again. I am not always the best at replying immediately, but I will get to your email eventually. And let's start the Q&A.
Great, thank you so much, Joe. We're going to start off with a question from your colleagues at the Woods Hole Oceanographic Institution. What was the density of the Wallops runaway munition?
Great question. It was right around, I don't have the exact number off the top of my head. I want to say it was about 2.5. And that would be in the Woods Hole scale, so normalized by the density of water.
Thank you. Another question from EPA. how are geophysical surveys, magnetics and electromagnetics, how are they integrated into the models you described?
So geophysical surveys provide really valuable boundary conditions for the models, whether it's a simple model or a more complicated or detailed model like Delft 3D coupled to UNMES, like the PEMS system. They all require some knowledge of the geophysics, and so they're important. Yeah, they all require it.
Thank you. And this is a question from the University of Rostock, all the way in Germany. Does the dynamic seabed burial model analysis assume full liquefaction of the seabed sediment?
So that's a great question. The initial iteration of the model that we worked with did assume full liquefaction, and we have now progressed to a second version of the model that allows for a degree of liquefaction. So no, where we are with our work right now, we do not require the bed to be fully liquefied to see partial burial or some burial happen.
Thank you. And this is a question from a Colorado regulatory agency. Can your modeling work provide insight or prediction into the depth to which munitions become buried?
So the question was, can we provide insight into the depth that they become buried?
Yes, yeah. Or prediction.
Yes. So I think that in a very first order pass, if you have a, say, coastal site, for example, you can look at the historic wave record and you can overlay that onto any one of the graphics that we looked at during the first half of the session and immediately make some estimate of burial or how much burial would have occurred or could have occurred at your site. Now, that assumes two things. You have some estimate of what your sedimentology is in the region of interest, and you have to pick what munitions am I interested in, because different munitions will have different densities and different calibers and behave a little bit differently. So you have to make some choices, but all of these graphics, these models that we presented can provide some prediction immediately.
Thank you so much, Joe. Maybe backing up a little bit, this is a question from the University of New Hampshire. Can you please identify the major event triggers for sudden munition exposure? That is, for munitions going from a long-term burial scenario to exposure.
Oh, so what can trigger exposure? So we started with an example, the very first two slides of the beach retreating, being in a sort of historic retreat, if you will, and that's, let's call it erosion, the same kind of process that happens, the same fate that happens during a storm, which is sand is taken from the foreshore and moved offshore. And so erosion events will expose munitions that are buried. Migration of sandbars, which happens during storms, can expose munitions. You have summer-winter profiles that are very typical of many coastal regions. I know our colleagues at Vieques Island observe this, and those changes in profile can expose munitions. And then what happens after that depends largely on the munition itself. So if it falls into this density category, it's likely not to go very far and to just be reburied very nearby where it was exposed. If it's in the swash zone, for example, right up on the foreshore, and it gets exposed during a storm, you know, anybody who's walked out on the wet beach knows it behaves like pavement. Things can roll around out there and get tossed around. And so it may work its way down the beach or get tossed up onto the dune or end up buried in the tow as well. But yeah, I think that's, you know, at least when we're focusing on coastal environments, those are your main mechanisms that come to mind.
Thank you so much, Joe. This next question is from the U.S. Army. How is the depth of liquefaction related to wave energy? You alluded to that a bit. Can you please elaborate?
Yeah, so it's directly proportional. I think you could say it's directly proportional to your significant wave height, for example. And so the way that we have modeled this, and this is fairly well explained, I believe, in the publication in the Journal of Oceanic Engineering that Dr. Klamler is the lead on, we had a pressure sensor close to the bed, but not on or in the bed. And we used that pressure value that we recorded under the waves near the bed to estimate the pressure at the bed. And then we take that value and estimate the liquefaction. So the pressures are large, and you can do it just by, I think you can get to it just from the significant wave height. I think it's directly related to the significant wave height energy. So I hope that answers.
Thank you, Joe. And a follow-up question from the same individual at the Army. Can a munition experience multiple liquefaction events?
I mean, I would say yes. So you could have one storm that comes along and buries it. You can have a second storm that follows behind it. I think even within a given storm, waves in nature and during storms aren't monochromatic the way they might behave in the laboratory, and they come in groups, and groups have different amounts of energy. And so certainly you can see multiple, I think you can see multiple liquefaction events. And I really hope that this is what we will prove to you with our observations that we're going to be making starting in December.
Thank you, Joe. We're going to take a few more questions before we wrap up. This is a question from New York University. Why isn't impact burial an issue that needs to be studied? Are the majority of the buried munitions a result of natural burial over time as opposed to impact burial?
So I have my own opinion about this, and I'll be clear that this is my own opinion about impact burial. I definitely think that impact burial has a role in completing our knowledge. And I think I said earlier, particularly in softer sediments, where impact burial is very critical to the final fate. But in sandy sediments, other than giving the munition a starting point for sort of the next large energy event to come along, that's really its role. And once that next energy event comes through and starts to liquefy the bed, or if it's partially exposed, starts to scour it and scour bury it, now the history of the impact burial is potentially lost, with the exception of perhaps some damage that it may have done to the munition, and then we get into a different space. But I do think impact burial has a role. I don't think it's quite as significant as some of these other mechanisms that we discussed today.
Great, thank you so much, Joe. This is a question from the University of Delaware. Since the bed elevation in the field may fluctuate, how do we differentiate between self-burial and bed form?
Yeah, so that's a great point. And it can be very difficult to monitor that fluctuation of the bed in the field during a storm event, for example. And all I can say is that we are very sensitive to this issue. And it was a large part of the motivation in how we designed the instrument package that we showed in the second half of the 81 millimeter surrogate that has the pore pressure and total stress sensors, because those sensors can tell you where the bed actually is during, or where the munition is, I should say, relative to the bed during these events, and tell you where the sea surface is as well. And so that's where we hope to help answer some of these questions, is with this new surrogate that we're going to be deploying shortly.
Great. All right, let's move on to some more general questions before we wrap up. A quick one from EPA. Have any current bay, river environments been modeled? Any high current bay or river environments, have any of those environments been modeled? For example, the Alaska glacial melt.
Yes. Okay. So for example, I am not aware of modeling that's been done with the Alaska glacial melt myself. I will say that rivers are getting more attention. And I think I can say this, that there is a new SERDP project that will be starting next year that's been awarded to Carter Duval to look at mobility and burial in high energy riverine environments. And so that is an area of, an opening area of research right now for the program office.
Wonderful, great response, and thank you for tying it into the other great work that SERDP is doing. All right, one last question. How do you envision the burial prediction information being used by groups working on Uxo detection and classification methods? And if you want to sort of summarize that, any last messages you would like to leave our audience with today, Joe, when you respond to this specific one, please.
Okay, great. So yeah, I certainly hope that these models for mobility and burial will be of use to other researchers working in the detection and classification realm. Particularly, I've been asked the question already by some of my colleagues if they should expect certain munitions to be oriented a certain way. And this question ties into a sort of a disconnect. That question is a disconnect between, my approach is to just understand, is it buried or not buried? Is it going to stay buried or not? Is it going to be mobile or not? They want to know, it's buried there. I see something there. I need help determining whether this is clutter or this is a real munition. And so to get to some of the details that I think the folks on the detection and classification side need, we will have to go back now and start to slowly, one piece at a time, add in some more characteristics of munitions, like where's the center of mass? Are these things nose heavy, tail heavy, or are they centered, are they massed very, is the center of mass right along the center of the tube, for example? And so that kind of level of detail will be important for helping them understand some of the details, but generally just being able to tell them that you shouldn't see things buried below a certain depth here or above a certain depth here after the storm has passed. I would hope that would be a really valuable starting point for folks doing detection and classification. And to just leave it, I want to just thank everybody again for the great questions from the audience. And what I really hope is that you take away from this webinar, we do have a good fundamental understanding of the physics of the phenomenology, and it really is driven by local environmental conditions, along with the munition of interest. What is it that we're trying to find? And I realize in some cases you don't always know what is out there. And I think we have enough understanding to provide the guidelines, even in those cases, to kind of bound your problem for you. The use of some of these technologies is still slightly over the horizon, but I believe it's coming. They're coming at you fast, and I hope you you get ready and are as excited as we are about it. Thank you.
Thank you so much, Joe, for a fantastic presentation and great engaging dialogue with our virtual audience members here, I would go ahead and like to wrap up and remind everyone that our next webinar is on Thursday, October 8th, and the focus will be managing AFFF impacts to subsurface environments and assessing commercially available fluorine-free foams. This webinar will feature two speakers. First, we'll have Dr. Damien Helbling from Cornell University. He'll talk about his work on developing and optimizing adsorbents to remove PFAS from groundwater, with PFAS being a major component of AFFF. Then we're going to have another speaker from Battelle, Dr. Satya Chalhan, and he's going to talk about his research on optimizing compressed air foam and ultra-high pressure foam delivery systems to improve the quality of commercial off-the-shelf fluorine-free foams. Registration is open for this webinar, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. And as we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you could please take a quick moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your attention.